By the way, the Wi-Fi looks like it's been working pretty well, but I just remembered to record anyway because our streams have been dropping in this classroom. So hopefully this works. It looks to be working, but we'll get you. And if you look back at the lectures, I already had to upload a recorded one, so you'll end up seeing kind of a duplication. 20 minutes worked last week, but I posted the full one later. Okay, sorry, just a distraction on my end here. So this partial ionization, we could say partial dissociation, or in some cases we might say complete dissociation if it's something like a salt, sodium chloride, really doesn't like to come backwards into sodium and chloride unless you have a lot of salt in solution. So solubility reactions are a good example. Technically, you could end up getting a saturation condition, but it's very unlikely. So it takes a long time before you get there. It takes a lot of salt before you start precipitating sodium chloride salt, table salt. So typically that would be a complete dissociation. Eventually, maybe it's a partial, meaning some of it stays as the whole, or some of it would stay as HOCl, and some of it as the dissociated components. So that's what we're talking about when we say partial or complete dissociation, ionization. So that's some terminology you'll see in some problems. Now, for a given equilibrium reaction, when the rate at which the reaction is going either direction, when those rates become equal, we've reached an equilibrium. So you could have a scenario where you have 100 pounds of something on the right and 1 pound on the left, and find an equilibrium because the rate at which they're heading in the other direction is the same. This would be a lot like saying you can imagine a little scale with a weight, and you think to yourself, okay, if we have 50 and 50 over here, of course, everything's the same. It should be equal, right? Well, what happens if we put 1 to 5? Well, you think, okay, that's going to change the equilibrium, but if we change it to 5 and also place it in a different spot, we might find an equilibrium. Okay, so the rate at which these things are changing is going to tell us when we have the equilibrium. So it's not necessarily the amount that's in each category, but the rate at which it's heading over to the other category. I'm going to give you there's a nice video online. We'll take a look. It'll elaborate on that, but it's this rate of change. You can think of it, if we use the banking analogy, if you're managing your finances and you have some rate at which you're spending money and some rate at which you have money coming in, it doesn't really, that those two rates have become equal and you've reached an equilibrium. Doesn't matter how much you have in that account or how much you owe or whatever, you've reached an equilibrium in terms of those reactions. Okay, many of these are pH dependent because we have a proton that will leave or add on, and so we will often talk about equilibrium reactions within the context of a pH. All right, so here's the illustration. Let me pull this up. I think this is pretty useful. And it'll take me just a moment to get the sound going. Assuming the internet works. Well, the internet doesn't seem to want to be working right now. It's not good for anybody viewing online. And not good for the demonstration. So I will do my best to kind of give you an example and show you what this video looks like. And of course, you're going to have this link online. So if you're confused about equilibrium, it's like a 2 or 3 minute video. This would be really a good idea for you to just go back and take a look. So let's imagine we have 2 containers. And each of them has some water in it. And you're going to take a couple of glasses or beakers and scoop water from one and pour it into the other. So in this video, the guy takes a couple of beakers, and at first he starts with a bunch of water in one and none in the other. And he takes and pours from each into the other. And he keeps doing that, scooping water into each of these beakers into the other one. Well, eventually, if they're the same size beaker, you end up with the same amount of water in each. Okay? So that's pretty obvious. So that's at time 0, and then eventually we get to here. Then he does something interesting, and I'm going to redraw this to make it a little better sized here. He does something interesting next and changes the cup size. So one is large and one is small. So the large one scoops more water every time until you run out of water and you only have a little bit of water left in the container. And then it can only scoop a little bit because you can't fill, like if you have a bucket of water and there's only this much water at the bottom, even with a big cup, you're not filling the cup much, right? So it becomes self-limiting. The reaction doesn't pour much water over, even though the rate constant, the size of the cup, could have allowed for a big pour. All right, and so essentially the small cup catches up with the amount because it's getting a full 100 milliliters every time, whereas the big 1 liter cup could only catch 100 milliliters at a time. So even if you change the size and have a large versus a small, you will eventually find an equilibrium. It's just that you will have moved more of the stuff over to the one with the slower rate constant. So if we think of this as the mass per time, so the rate of exchange, these rates become equal, and we've reached equilibrium. All right. So the way we describe this, and it looks like I have internet for a moment, so I'm just going to see if I can possibly give you a moment of this. We'll see.
The very next time
Well, that's not pleasant. I'm sorry. So you can see he's got 2 buckets. Okay, we're not going to try this. Sorry. You can see. You could do the demonstration and play with it for yourself. I gave you the best shot I could. All right. The reactions and the products we typically will label similar to any other chemical reaction with some reactants on the left and some products on the right. Convention would be to call these A, B, and C and D if we have 2 reactants and 2 products. So we will describe that with a lowercase a as the number of molecules there of A molecule, so molecule A, and then B of B, and so on. So when we wrote, let's say, our butane, 1C4H, is it 10, I think, plus some number of, I guess it was, maybe we did 2 and 9 or something, or 13. Something like that. This would be lowercase a would be the 2, the A is the butane, and then the lowercase c would be the 13 for the oxygens, and Cu is oxygen. Okay, so that's what I'm referring to when I'm describing these. Now, when we write an equilibrium equation, what we're going to say is we have some constant that is the balance that says, okay, here's the balance between these two rate constants to say to what extent are these moving in one direction or the other. That will be a constant. We can say this is an equilibrium constant and set that equal to the products over the reactants. Now, the way we set it up mathematically is the concentration of C, one of the products, to the lowercase c power. Many times these will be 1, and you don't have to worry too much about it. But that'll be an exponent here times, and make sure you don't add these. I see people make this mistake every time, so make sure you're not adding these. You'll have this on the formula sheet too. So make sure you don't mess this up. This will be a multiplied by. So these are molar units. They have brackets, therefore they must be in molar units, and they are multiplied by each other. That's the product of the products over the product of the reactants. Okay, so C times D over A times B. All right, with that defines the equilibrium. That by definition, if we know the constant and we know something about the reactants, then we know something about the products. Okay, it's just a ratio that is given, and we know that. There's one little caveat. If we're doing an equilibrium with, let's say, water or with some solid and a solubility product, that goes to 1. We just say the concentration of a liquid is 1. It's just so much that it's essentially ignored. Don't worry too much about that. We'll see that in the example for water in a moment. But in general, if it's a solid or a liquid, we just treat it as 1, and it kind of disappears. Okay, for these reactions, and again, that video might be helpful if you're trying to understand this. It might take a little bit of time to reach that equilibrium, and in that video, he pours a few times before you reach there. But for our purposes, we're not going to worry about that time difference or the rates of how quickly we get there. We're just going to, when we do an equilibrium reaction, we're going to assume we've reached equilibrium. So that uncomplicates it quite a bit. All this mass balance stuff and rate constant stuff, we're not going to worry about the time getting there to equilibrium. I just want you to be able to understand what the equilibrium is telling us once we get there. So we will pretty much have equal rates. And if you need a conversation, please go ahead out. It's distracting me a little bit and probably your peers. So I don't mind if you're not here, attending somewhere else, doing whatever you need to. Just please no conversations while I'm doing my thing here. When you get to your equilibrium, what I said earlier is there's not necessarily equal amounts as we see, here versus here, but the rates are the same. Okay, when we take some example of some chemical in water or in some other solution, but we're just going to deal with water, and we take a look at how this equilibrium plays out in terms of what species it's in, we will be able to plot, okay, what portion of this is in the acidic form or in the basic form. So if we plot the portion, the fraction, we often call it alpha fractions, don't worry too much about that, in this case, we're doing carbonic acid. This is basically dissolved CO2. So this is what happens when we take CO2 plus water, gives us H2CO3. This is basically in every bit of water that's exposed to the atmosphere. Now, when we add it to water, it's in that form, and then it can give up a little bit of some protons, meaning that as soon as we put pure water in the atmosphere with a little bit of carbon dioxide, it will become mildly acidic just by this reaction alone. So rainwater is slightly acidic, it's pH 5-ish, or a little higher. So what happens is we can see that at any given point, let's say we set the pH somewhere, our equilibrium between these species will be dictated, and we can see there's some portion. So at pH, let's say 5.5, we will have an equilibrium between this carbonic acid and what we call bicarbonate, HCO3-, and about 90% of the total carbonate will be in the form of carbonic acid here, and about 20%, or excuse me, 10%, whatever's remaining, will pretty much be in that. Or maybe I should draw it that way. So what you can see here is at a given point, where we're at equilibrium, the pH is kind of telling us what's the portion. At some spots, we will find an equilibrium where the amount on either side is also equal. So it's approximately 50-50 when we're at pH 10.3, I think is the value. And that's a particular and important spot we would call the equilibrium constant between these two. So our Ka, in this case I'm going to say 2 because this one would be Ka1, would describe the moment where CO3 2- as a concentration is equal to HCO3-. In other words, we can write this as the equilibrium reaction if we say Ka2 would be our products over reactants, our products being, well, let me write the reaction first. I'm going to make a little space here. Our reaction here is HCO3- is in equilibrium with H+ and CO3 2-. So with this, if that's our reaction and we want to describe or define our equilibrium constant, we can write it as the products. And you'll notice we have just one here in front, just one here in front, and just one here in front. So each of the exponents will simply be 1, and it will end up being the products, H+ times CO3 2-. If we want to, we can raise each of these to the 1 power, just to be very clear, divided by the reactants, which was the HCO3-, again to the 1 power. So that's our equilibrium equation for this particular reaction, the balance of these two out here on the right. If you wanted to solve for Ka, you could take a look at the H+ value. We'll talk about this in just a moment, but you can get H+ from a pH. You all learned this at some point, and I'm going to remind you of it exactly how it works in a moment. It's just a log system. It'll be very clear in a moment. You can grab that H+ concentration from our x-axis, and then you can pretty much find the Ka value. In fact, when these two are equal, one over the other is equal to 1. So the pH at the point where they meet is the Ka value. So at this point, pH equals what we call the pKa, or H+ would be equal to Ka when these two are equal. Okay, so that's an elaboration on how those pieces connect together. If you get lost at all, just remember that here's your equation, and you should be able to take any equilibrium reaction, put it into there, and if you do that properly, you're good to go. Yeah?
Are you calling it Ka because
Yeah, the convention is to call this, instead of KEQ for a generic equilibrium, since it's an acid exactly, it's common to call it KA. So for you, I probably should have been writing KEQ. You'll see it as KA. You'll probably see it in problems. Thank you for that clarification. That's exactly right. Yeah. It's going to represent, if you imagine the hypothetical scale that I was drawing, like something like this, it's kind of going to represent where we place the balance mark between them. It's essentially a combination of the forward and the backward reaction rate constants put together into one constant. So it's going to say, like, if this is our K, then sometimes we will have one that is shifted to one side or the other. Okay? So it's kind of telling us what it takes to make that balance. It's a constant, just like any reaction rate constant. Yeah. Yeah, it is essentially coming from, if not equal to, the balance of the two rates. And it is, if you really want to get into it, it's coming from thermodynamics, which is typically how we understand how much reactions will occur. So we can derive this from thermodynamics. I'm not going to make you guys do that. We do teach some of that in a slightly more advanced class. So if you want to, let me know. I can hook you up with some materials and teach you more about that, but I'm not going to make everybody suffer through that. But it is thermodynamics coming exactly from how quickly it happens. And if you think about that example where you're scooping water, you can find some rate constant or some equilibrium constant, and it will be a function of how big the two jars are, right? If one's small, that's going to tell us where that balance is showing up. And that'll depend on the chemistry of the problem. Any other questions? Okay, so I've been talking about pH. Let me give you a thorough reminder here how water works and how pH works. What does this P mean? I even said pKa or pKeq. Well, the P is just a function. So when we talk about water, water is in equilibrium with H plus and OH minus. H plus being essentially what we consider as acid or acidity. OH minus then would be essentially base or basicity. So if H plus is essentially acid, we can think of OH minus as the stuff that makes a basic chemical basic. We have an equilibrium equation for water. Believe it or not, you're familiar with this. This Kw, so it's the Keq for water, is equal to 10 to the minus 14. If you recall, pH is on a 0 to 14 scale. This graph doesn't quite show it, but typically we would put it all the way out to 14. The reason is because the equilibrium for water has a Kw of 14, and it turns out that if we look at this equilibrium reaction with water being able to dissociate to H plus and OH minus, partially dissociate, right? It's an equilibrium reaction. Well, the reactant itself is water. So H2O as liquid water will react, and some of it will become H plus and OH minus in some combination. It happens that not a lot of it does that. As a portion, we still have many, many H2O molecules in our water, no matter how acidic or basic it is. So what this is telling us then is, based on our assumption earlier, there's so much water that when we take away a little bit to form some products, it doesn't really change the concentration of the water that's still there. So we're going to treat this as 1. It's a little more theory that we could use to describe that, but that's a good enough for us right now. So then, since it's a liquid and is essentially not changing in reference to the other stuff, we are going to say that Kw, which is 10 to the minus 14, is equal to the concentration, the molar concentration of H plus times OH minus. Now, what pH do we find do we describe as neutral? 7, right? So probably everybody remembers that, or when we say that, it's like, oh yeah, duh. So if pH is 7, that means we have a neutral amount of acid and base, because we said that's the neutral case. So when the H plus equals OH minus, that we could then say that under that condition, first of all, we were saying that's pH 7. We would also say that H plus squared equals 10 to the minus 14, which means at pH 7, H plus equals 10 to the minus 7. Okay, which also would mean OH minus equals 10 to the minus 7, because they're equal. So what we see here from this equilibrium constant of water, you notice the 7, it's 10 to the minus 7, and pH 7, well, you've just discovered what the P means. When we say P of something, we're just saying take the negative log of it. So negative log of 10 to the minus 7 turns out to be 7. So P of some quantity that is 10 to the minus 7, the negative log of 10 to the minus 7 equals 7. Okay, so we can take the P of X, we can take the P of OH, which would be essentially the inverse of pH. It's the amount of basicity there is. We can take the P of some equilibrium constant. And that's just a log transformation, taking the negative out and taking the log of it. So when I said earlier that down here we have a pH of about 10.33, it's because I happen to remember, and when I'm seeing this, it lines up, and I'm like, oh yeah, I think that value is about 10.3. The pKa would be 10.33 because the pH is 10.33 at that spot. So that's why I wrote it by saying pKa or pKeq, because we're on that P scale. So one thing you'll notice about the pH scale is it's a log scale. So 10 to the minus 7 is a lot different than 10 to the minus 8. It's a complete order of magnitude change, even though we only are going from 7 to 8. So that's just another thing to keep in mind with acidity. Okay, does this make some sense with pH? Any questions? All right, so if I ask you to solve for what's the H plus concentration of a solution that's pH 4.3, can you do it? Okay, some of you yes, some of you, everybody yes. How about the OH minus concentration if I tell you the same thing? That would make you use this equilibrium constant. So make sure that you remember, and this is another one piece you probably ought to commit to memory. I'll probably try to remind you on an exam, but the K for water, equilibrium constant for water is minus 14, 10 to the minus 14. So pKw is 14. So this would be a good one to remember. Anytime you're dealing with pH and you need to solve something for base and you have acid or vice versa, that would be good to know. All right. So with that, I want to get on to the fundamentals of water treatment. All right. So in general, if we want to know whether or not we can drink water, it's a little bit obvious, right? We don't want it to make us sick. So if I'm going to drink this water, I kind of want to know what treatment it's had or where it's been, because I want to know what's in it. Does it have pathogens in it, or is it safe for me to take a sip? Right? So the most common or fundamental issue with water is what we would call the fecal-oral route of transmission. So you're going to have to suffer for a moment through my drawing skills. If we imagine some river and we perhaps want to take from this river and grab a glass of water and drink from it. Well, our entire water treatment system is designed to make sure this is protected from what we call the fecal-oral route of transmission. So it turns out that most rivers, upstream somewhere of most rivers, we're going to have, unfortunately, some sort of discharge of waste, right? So if you can't tell, I'm drawing a little toilet. And eventually that's going to make its way into our river. This is why we call it fecal to oral route of transmission. Many food and waterborne pathogens are coming from something else's warm-blooded gut. So our body temperature is about 37 Celsius, 98 degrees Fahrenheit, and that happens to correspond with many other warm-blooded animals. So anything that has a warm-blooded gut grows a bunch of bacteria in their gut to help with the digestion. Those are the types of things that could cause us a problem if they get to the wrong spot in our guts, right? So if we consume something that is going to cause us trouble, then we have trouble, right? So that's where drinking water treatment comes into play. We want a barrier here to prevent that. We want multiple barriers for our to interrupt this route of fecal-oral route of transmission. So here would be our drinking water treatment. So the most fundamental component is simply interrupting that. Now, as it happens, we could also say we've got wastewater treatment here. But even that's not enough because we might have little stick figure animals also excreting. I don't know what kind of animal I'm drawing, but there we go. We'll pretend that's an animal. And also contributing to this potential for fecal-oral route of transmission. So it doesn't have to be necessarily human waste that is the problem. So we have essentially two barriers. Both are helpful, and both are going to do more than just that, just pathogen control. But in general, this is the most fundamental, and this is where we kind of start. And as soon as we discovered the germ theory of disease and understood this was a risk, that's essentially when we began to solve these problems. So where we get our water matters. If you happen to go hiking and find a glacial snow melt on the top of some mountain, there's a pretty good chance that there's nothing but water there and no warm-blooded animals excreting into that. Sometimes you'll find a pristine mountain spring coming straight out of the mountain, and it's going to be coming from rather pure groundwater, and maybe that's safe to drink too. So sometimes you'll find scenarios where it's pretty safe. You might think, okay, well, maybe I'll capture some rainwater. That could be pretty good unless some birds have been, pooping in your rainwater collection system, and then you've got some potential problems. And not to mention whatever dust and aerosols might be accumulating and bringing in stuff maybe you don't want to drink. So it really depends. Where are we getting our water? What kind of treatment do we need? In Baton Rouge, for example, we have a pretty good groundwater aquifer that's deep. It's rather isolated from any human or animal activities. And it's a nice freshwater basin. So when we pump it up, we typically just chlorinate it to make sure our distribution system stays clean, and anything that might have happened to find its way in there that would be a problem would be killed. And we can basically just send it along. So there's a lot of filtration of particles just from the ground, the soil particles themselves. So in that case, we don't need to treat a lot, but it's a little different from the scenario in New Orleans where they don't have access to an aquifer that way. Instead, they're going to take from the Mississippi, and it's a bit dirtier, so they're going to have more treatment. So as we think about what kind of treatment we need for water or even wastewater, those are the types of things we would have in mind. So I think I already gave you this overview, but essentially we are going to be treating the water here prior to distribution. Even the distribution system itself may be considered part of the treatment system because we want to make sure that it stays clean. If we have some interruption, a water main break, or somehow a pressure loss in the pipe system, that becomes an issue for the net treatment of what the quality of water reaching people. It turns out we would much prefer to have highly pressurized water pushing water out of the pipes if we have a leak than allowing for anything to leak into the pipes from the ground. Because what else is in the ground? Well, maybe sewer lines, maybe dogs that were, pooping on the lawn nearby, who knows what. So we always want to keep water pressure to keep water moving out rather than into our water distribution systems. So if we have a pressure loss for some reason, maybe power outage or equipment failure, that will typically trigger a boil water advisory for whoever's downstream for X amount of time so that we can resume clean water through there. So if you see a water main break in your neighborhood, you might expect that you ought to be getting a boil water advisory if that's an impact to you. Likewise, we would generally prefer to, speaking of equilibrium chemistry, when it comes to pipes, especially metal pipes, we can either allow mineral accumulation to constrict them slowly over time. That would be kind of a precipitating type of scenario where it's slightly alkaline, encourages mineral deposits, or we could do the reverse and have the opposite, slight erosion over time. We are always going to prefer slight accumulation, slight narrowing over time. It will eventually ruin our infrastructure, but in a way that's not causing us to have these leaks. So you'll see, if you look it up, photos of pipes that have been in the ground for 50 plus years. They'll have a bunch of minerals on them. And that's actually the way we prefer it, because we could dissolve the minerals, but then we're eventually going to dissolve our pipes too and have leaks. Okay, at any rate, what we're looking at is we're going to focus in on what is our water treatment and where to begin with that. So we'll get to sedimentation in a moment, but just a couple other quick notes. If you think about when, or take a look at when we began chlorinating, it corresponds pretty well with the change in how much disease we have. So historically in the US, we had quite a few deaths per 100,000 population from typhoid. So 20 to 30 per year. For some time, we began chlorinating. This was probably not every single place, but this was generally when the practice began. Along the same timeline, we were cleaning up our wastewater as well. So both barriers were improving. Our medical care for typhoid fever was likely also improving, so we could probably put the advent of penicillin on here, probably also corresponds nicely. Just to show you that each piece here is part of the picture. Today, if you travel to certain places, they might recommend you get a typhoid vaccine in case you are exposed to essentially typhoid from a fecal-oral route of transmission, because not everywhere has the same level of control with chlorine or with whatever other treatment as we have here. So when I'm here in this building, I have no problem drinking the tap water. I do pretty much every day. If I go to certain other countries, I'm probably bringing something to treat it, or getting bottled water that I'm confident has been treated. And then I will not have any ice from, if I buy a drink, let's say I wanted some, instead of getting the tap water at some restaurant, I will not get a Coke with ice or a tea or something. I would get it without the ice, because the ice coming from some ice maker from the tap water. And turns out freezing stuff, biological things, doesn't necessarily kill them. Maybe occasionally a little bit, but usually we use that to preserve bacteria. So freezing is not something that would kill your typhoid, for example. Okay. So what are our regulations look like? Well, we have two general classifications. One would be our primary standards. These are what regulates anything that can impact health. And we've talked a lot about pathogens. We're going to include toxins in here as well. So anything that could in some way poison you, that would be included in these primary standards. So primary meaning you must do it. These are enforceable by law. If you're not caring for these things, then you're in trouble. We might look at chemicals, radionuclides, and microbial categories of contaminants that could be a problem. Now, there's an entire secondary set of standards that are not enforceable, meaning they are optional. Recommended, but optional. So, for example, how many of you, and maybe, did I already ask you this? How many of you like to drink brown water? Yeah, I already asked you this. Okay, so we started the class that way. Turns out that we don't want brown water coming out of our tap, even if we might like drinking tea. So these are not enforceable, but certain ones of them are can be important or can be indicators. All right, so that means I probably already showed you this slide. The hardness of water. This is essentially how much mineral content there is. This varies depending on where you are, what kind of groundwater you have, or what minerals are around. So you might look and think to yourself, where have you visited? I'm sure there are maps for other countries too. And consider, oh, have I experienced hard water, soft water? What's the deal? If you try water in Baton Rouge, it's generally fairly soft. But maybe if you're down in New Orleans, you are drinking a different water supply or experiencing it, might feel a little different. Okay, so where do we begin? Well, I mentioned earlier the cheapest thing to use would be gravity, right? Kind of do nothing. If you can use gravity, we're going to use gravity. If we have the space to allow things to settle, that's great. So a typical treatment plant, first we're going to probably realistically screen out any large stuff with some screening racks or bar racks, something like that. And then we're going to let gravity take out any particles that are large enough, heavy enough, dense enough to settle. So we'll have what we call primary sedimentation. That's what we will talk about, we'll begin speaking about today, how to arrive at an equation that tells us something about how quickly can we settle stuff, how effectively can we settle things, given some flow rate, given some volume, what size of a sedimentation basin do we need. After that, the next best thing, and what you'll find here is we're always going to look at a cost-effective, reliable way to treat our water. That's ultimately the goal. We don't want to make our water cost a bunch, and we want to make sure that it's safe. So in terms of engineering, in some way it gets a little boring because at this point people are like, if it ain't broken, don't fix it. Chlorine works well enough. Let's not do anything too fancy, right? That's a general mentality, and typically that's a good thing in terms of if it is giving us safe water, let's keep getting safe water for cheap. So the next thing we can do is a little fancy. It takes a little chemistry, and we encourage particles to stick together so they become larger, and then we can use gravity a little better. So we're going to first use gravity for what we can, then encourage particles to stick together, make little particle parties, and fall out a solution later as larger aggregates. And this is what we call coagulation and flocculation. So a coagulant is the sticky stuff, almost like glue, letting the particles grab each other. Talk a little bit about that. And then we'll use sedimentation again. Turns out that in wastewater treatment, we also use sedimentation. So in that sense, what we talk about next couple of lectures will also be relevant there. So we're going to do sedimentation typically twice. Occasionally we might change this up and only do a filtration in the second part. So this is just a generic, typical surface water treatment plant. It's going to be a little different for groundwater treatment because we're not going to have so many particles, for example. But this is just a good overview of what a typical plant will look like. Then we'd probably go on to some filtration, ultimately some disinfection, and make sure it's good for going through the distribution system. All right, so I'm going to pull up some slides on sedimentation then. and we'll begin on that. All right, so here we go. Let's use gravity. Well, if we imagine a random particle floating around in water, it's probably going to be some weird-looking, strange, who knows what particle, and who knows how much it weighs. So we're going to make some assumptions to model sedimentation, and it turns out these are actually reasonably reliable and useful when we are designing systems. So first of all, we can assume it's a perfect sphere, and that for any type of particle that we're trying to settle, usually we'll have some target in mind. Let's settle everything that's about 10 microns, micrometers in diameter or bigger. So usually what we can do is assume something about the particles that we're targeting, and given that that's the size we're trying to remove, and we know that we have to treat anything that's not removed by gravity, we're going to just have to design for that. So it's okay to make some assumption to say, let's assume that they're spherical. I just like the blue a little better. And maybe also that they're the same size and density. Okay. If we do that, then we can get some relatively simple math, and we're actually going to derive that here. So as you can see, we're going to have a few forces acting on any given particle. First of all, of course, what we're aiming to use is force of gravity. So that will be a force vector in the downward direction. And then we're also going to have a buoyant force based on the mass of water displaced by this particle. We'll describe this as FB. So if the density of a particle is less than the density of water, it's not going to sink, it's going to float. Turns out that you can design what we call DAF, dissolved air flotation systems, to put a bunch of air, tiny bubbles in the water that will grab onto the particles, or the particles will stick to the air bubbles, and then you'll float them. So you can actually design a reverse sedimentation basin, and you'll have basically the same principles, just with floating particles instead of sinking particles. Still actually using gravity or essentially these effects. Okay, at any rate, typically we're going to use gravity and denser particles, and that's the math that we'll take a look at. You'll see that it's plausible to do the reverse. But assuming that we are traveling with our particle in the downward direction, then we also have a resisting drag force in the upward direction. So we're going to have two forces upward. This force of drag, as you can imagine, will be proportional to the size of this particle, the surface area, and the speed at which it's going. All right, so with three forces, essentially what we want to do is find a terminal velocity. And you can think of, if you've ever been skydiving, anybody ever gone skydiving? Okay, one person. Anybody ever been swimming? Okay, probably most people. You can imagine if you are diving through the air or through some liquid, you'll reach a terminal velocity at some point. And if you're skydiving, if you put your arms out, you'll feel more drag than if you're like doing that. Okay, if you're driving along or biking along and you put your hand out the window or something, you'll feel the drag. Okay, at some point you reach a terminal velocity and the forces have matched, you'll reach that equilibrium. And that's kind of what we want to look for to give us a velocity of our particle. So I'm going to say, we'll call it VA for terminal velocity. That will tell us how to design our sedimentation basin, because we know how fast the particle's sinking, meaning how big of a space do we need to let that sink given some flow rate. So that's essentially what we're going to target and derive. This will depend on, the force of drag depends on this. And so that's how we will be able to find it. So if we define our force of gravity as mass times acceleration, mass of the particle times the acceleration due to gravity. I think I have all of these parameters written out nicely here, so I'm just going to give you a big picture overview. I'm not going to define each one of these right here because it's on the next slide. So mass times gravity is our force of drag. However, it's difficult to weigh one little particle. In fact, it's probably impossible to weigh a tiny little particle, especially when it's floating around in water. How do you even grab it? So without going too much into the technology that maybe could do that, an easier way to do it would be to observe what size it is and then make some estimation or to make some bulk calculation about its density. And so you bulk density is something maybe you can get, and the particle size is something you can observe with some either a filtration or even a light scattering technique. It's pretty handy. So we can easily get a bulk density and a particle size, or maybe we're just simply designing the system for some size, like I said earlier. Let's get everything 10 microns and bigger. That's now our design criteria. So if we're doing that, then we can use, instead of mass, we can use the density of the particles and their volume to get the mass. So instead of weighing them individually, what we're going to do is, instead of mass, we're going to use density, because density is equal to mass per volume, right? So with that, if we multiply the particle volume by its density, that's mass. So that's what we're doing here. This is just a term giving us mass. Still using acceleration due to gravity. So that's our force due to gravity. Our buoyant force is almost the same, except instead of the mass of the particle, we are using the mass of water displaced by the particle. So another reason to use the volume term here, because we need a volume to understand how much mass of water we are displacing. So mass of water, this is going to be, so rho will be the density, and this would be rho for a P would be for the particle. And if we leave it off, just rho would be for water. It's just how our book does it, so that's what I'm doing. Again, all of this is written out on the next page. Okay, so we have a buoyant force that's almost exactly the same as our force due to gravity. And remember that it's the amount of mass. If we take a balloon underwater or a beach ball and try to force it underwater, it takes some force, and actually the force that you're pushing on it is equal to the weight of the water it's displacing. So if you take a baseball, or let's say a baseball-sized hollow ball that's pretty lightweight, you'll feel, okay, it takes some force to push it under. And you take a giant beach ball, and there's no way you're going to push that under because you're displacing so much water, it's taking a lot of force, okay? So the same thing's happening with these little particles. You've got this upward force, but it's in association to the water trying to push that back up. Now the force of drag, this is coming from, again, the surface area and all of that. So if we take a look, this is going to be 3 times mu, which is the dynamic viscosity of water, times pi, times the settling velocity, I guess Vs, I'm sorry, I said VA. Let's do Vs. Vs, and that's the term that we care about, times the diameter of the particle. So this is the formula for the force of drag. I think we could arrive there by taking the circumference and all that, but we're just going to take it for granted that's the force of drag. Okay, I'm not going to bother deriving the physics for that. I've forgotten it anyway. So that's just what it is. But what we see here is that the velocity term is there, and that's what we want to solve for. So in order to solve for that, all we really have to do is find the scenario when the force of drag plus the force of the buoyant force is equal to the force due to gravity. This is where our terminal velocity happens. When all the forces upwards equal all the forces downwards. And then solve for V. So that's what we'll do. And when we're using these volume terms and the other terms, it's actually not too complicated of a thing to do. So here they all are written out. So you have each one of these. Mu is a dynamic viscosity of water. Units are kilogram per meter per second. You'll see when we have the table that I showed you already, many times this is expressed as 10 to the minus 3 kilograms per meter per second. The settling velocity, we're just going to go ahead and put everything in meters, kilograms, and seconds. So the settling velocity then we will use as meters per second. The diameter of the particle then we need in meters. Many times you'll see it in micrometers, so it's up to you to remember micro is 10 to the minus 6 of something. So a micrometer, 10 micrometers means that's 10 to the minus 5th, or 10 times 10 to the minus 6, however you want to write it. Acceleration due to gravity, you probably ought to remember this is 9.81 meters per second squared. So make sure you remember that. Volume of a particle, that's going to be part of a problem, most likely. Or maybe we calculate that given some, you'll see that it's going to come out in the problem with diameter can be converted into volume. And density of the particle, density of the water. We have a lookup table for density given some temperature. So viscosity and temperature will have viscosity and density will both be impacted by temperature. Okay, so to put all these together, let's derive it. So we said we need the force of gravity equal to the buoyant plus the force of drag. I'm just going to go ahead and start solving for the Vs. And what I'll do is take the force of drag, just subtract the buoyant force from both sides. So I'll say 3 mu pi times diameter of the particle times Vs is what I want to solve for, is equal to the force of gravity, mass of a particle, times, and in fact, I'm not going to start with the mass. I'm going to start with the volume. So Vp times the density of the particle times g. That's our F of g minus the force, the buoyant force. So again, we have the volume of the particle times the density of water times g. So there's a few terms that are the same on the right, so we can factor a couple things out. I'll go ahead and do that and say we've got the volume of the particle times gravity times rho particle minus rho of the water. Now the volume of the particle, we could use that, but it might be a little simpler and it will be handy to go ahead and put that in terms of the diameter. So volume of a particle of a perfect sphere, so let's say volume of a sphere, anybody remember that? Four over 3 pi r something? Okay, so and if we want to change that to diameter, we would say 4 over 3 times pi times diameter over 2 and cube that whole thing. Should give us, so 2 cubed should be 8. 8 times 3 is going to give us 24. 4 over 24 is 1 over 6, right? So we should be able to convert that to diameter just to be kind of in convenient terms. We will then say volume of a particle is equal to 1 over 6 times diameter of the particle cubed with a pi. Okay, fair enough? All right, so given that, we can then substitute in here and say, just for a moment longer, I'm going to keep the left side the same. 3 mu pi times diameter of the particle equals, and here I'm just going to say pi over 6 times dp cubed times g times rho particle minus rho of the water. Okay, so now you can see we can simplify things out pretty nicely. If we divide both sides by the pi, those will cancel. Divide both sides by mu, mu will come to the bottom. Divide both sides by 3, we'll get 18 on the bottom. Question?
I don't know what happened to the S on the left side.
It's still there, just hiding. Thank you. There we go. Hiding in my imagination. Okay, then we can divide both sides by the diameter of the particle, and that'll change from a cube to the squared. So at the end of the day, our velocity equation, which you'll have on your formula sheet, will look like this. And the reason I'm deriving this is so you can kind of get a good feel for where this is coming from. Even though I'm giving you on the equation sheet, I think it's kind of nice to be able to see, hey, this is how we could find the terminal velocity of a skydiver or a particle in water, right? Okay, so this will be, I'm going to go ahead and write it as g, just to match our formula sheet exactly, times rho of the particle minus rho of the water, times dp squared, divided by 18 times mu. Okay. All right, not so bad, right? We get a velocity term based on the characteristics of some particle. We have to know a little bit of something about the particle, or perhaps know what kind of particles we must remove, and then we can get there. But that gives us a convenient way to work with it. Now, one thing I'm going to note here is this diameter of the particle makes a big impact on how fast it's settling. So just looking at it as an equation, if we were to change one parameter in order to make it settle faster, well, we could change the force of gravity. You know, we could try going to the moon. We could try centrifuging it. So if you've ever worked in a lab with a centrifuge, what you're doing is artificially inducing some acceleration, that centrifugal force acting kind of like gravity. We could imagine trying to do sedimentation on the Death Star. What kind of gravity do they have? You know, there's all sorts of gravity terms, but that's not usually very convenient to change. Maybe if we're on Jupiter, sedimentation might be pretty easy. It may be a little overbearing. Okay, how about the density? Can we make particles more dense? And if so, it's actually similar to gravity in that it will have an impact, but just like a multiplicative impact. You know, if you multiply the density by 2, then you're multiplying the settling velocity by about 2. If you multiply gravity by 2, it's by 2. If you multiply the diameter by 2, you've got a square here. So you are making a much bigger impact for doubling the diameter than you would have for doubling anything else. On the bottom, we have viscosity, so maybe changing the temperature could change that a little bit. If you decrease the viscosity, it tends to decrease with increasing temperature. That could change. If you've ever noticed trying to sediment something through some honey, if you drop something in honey, it's going to sediment very, very slowly due to the viscosity. Okay, so maybe you could have some impact, but for water treatment, not really. So the one key thing here is if we change something, that particle diameter makes a big impact. And that's really coming from the math of how the drag force and all these things end up balancing. So the sedimentation velocity is the real piece to change if we're going to be smart about the physics. So dP, so big impact on Vs. Okay, good with that. All right. So that brings us to sedimentation. And how do we put it into practice? I'll just start with this slide, give you a little overview here. Typically, and we'll get into more math next time, and it is actually quite simple math. Once we get it to this point of a settling velocity, it's pretty simple. So in practice, we almost always use either a rectangular basin or some circular basin that's going to act a little bit like a rectangle if we stop and think about it. So essentially, if we take a cross-sectional view, even if we take one of these circular, cylindrical type clarifier systems, even if we take a cross-section of that, let's say from here to here, we can still draw it as a rectangle. So if we take a cross-section of our box-shaped sedimentation chamber and we just take a horizontal look at it, so as if we are standing on the ground and looking that way at it, or if we take one of these cylindrical clarifiers and identify along one radius what's happening from the middle point to the edge, what we're looking at is how is the particle settling as water travels either from the center of this to the outside or from one side of the rectangle to the other. So water is going to travel, and this is going to be our height. And we can imagine this has some reactor dimension. It could even be a circular one, right? This could be one of these. The middle point won't have a circle. Could be from the middle and circling around, or it could just be like that. In either case, what I'm showing is that we're taking that cross section, going up is the height that the particle has to fall, and then what we'll be looking at is a given particle and its trajectory downwards as the flow rate is going through to the side. The particle will then travel like that, well, in a straight line, right? So the particle will make some journey to the bottom, and when it hits the bottom, it's going to get stuck, and we will have settled it. And water, by the way, we will be taking typically from the top of this thing so that we're avoiding any particles that are near the bottom. So in a sedimentation chamber, we can then do the math about how fast is that particle settling, given what we just derived. And given some flow rate, we'll take a look at how to design this chamber to make sure that it hits the bottom before the water leaves. It ends up being pretty simple. I'll explain the logistics of that next time. There's a little overview for you. Okay, so if there's no questions, we'll see you on Thursday.